Welcome back, everybody.
Thank you. Welcome back. So this is the Chapter 5 review. Ooh, let me get the other screen rolling. I heard some seniors say, "Oh yeah, it's 4-9 weeks. Nothing really matters anymore." So be careful. Be careful. It's like, oh, it's 4-9 weeks. I'm already into college, so it doesn't matter. Be careful. If you're in CCP classes, it definitely does matter. 2957. I had to remind some of my comp students that, okay, don't forget that if you're in CCP, this grade goes on your college transcript. It factors in toward your college GPA. So just be careful about that. Good and bad. I don't think anybody's, none of you guys would say that, right?
I've still got 9 more.
Yeah, you guys are
Stuck here.
Yeah. Sorry. All right. So the Chapter 5 test, which is tomorrow, just covers sections 1 through 4. So I just kind of wanted to outline the things that you'll need to do in there, and then I'll go through the review. All right. So section 1 was an introduction to the normal curve. That talked a lot about the properties and the basics and when to use the normal curve and so forth. And then we introduced the z-score table and areas which would relate directly to probabilities with z-scores. Section 5.2, finding probabilities with z-scores. That's just basically taking an x value and saying, okay, what's the probability of getting bigger than this value? Take that x value, subtract it from the mean, divide it by sigma, and that'll give you your z-score, which then will take it to the table. Remember that you'll have to do, probabilities when it's greater than this, which would be 1 minus the z-score. Probability from the z-score, probability when it's less than, which would be just taking the probability off the z-score table. Ooh. I'm getting a phone call, and I don't know who it is. It's potential spam. I might have to take it real quick. Hello?
All right, guys. So number 3 is finding values given the percentage of defined x value. We have x equals mu plus mu to the O.
Also, you can give us a call back on our same number. Thank you for your time.
Just give them a call back.
Also, you can give us a call back on same number. That's spam. It was not potential spam. It was spam. Yeah. I always have to take phone calls just in case my kid gets sick or something and I don't recognize the number that somebody's calling from. So again, finding probabilities, you got to think about, whether I want it to be in between certain values, to the left, to the right. Just kind of plan accordingly, use your logic, use your brains. Section 5.3, it's kind of like the reverse of section 5.2, where now I say, what would, starting with this probability, what would be the x value that pertains to that probability? Given the percentage, find the x value, and the formula there is x is equal to mu plus z sigma. Mu plus z. Come on, get off of there. Thank you. Mu plus z sigma, and that will give you the x value that you would need for any certain value of percentage. Remember that's where you start with the percentage, say 95%. Then you go to the table and you find a z-score that pertains to 95%. And then you take that z-score and you put it into that formula. Mu plus that z-score that you find given that percentage times your sigma, and that will give you the x value that you would use. And then, we had our quiz, 5.1 and 5.3 quiz. So make sure you take a look at that. A lot of you did really well on that. Take a look at that quiz, because that's really all the questions I'm going to be asking from section 5.1 and 5.3. Excuse me. And then section 5.4, that's when we kind of switched gears, kind of changed our focus and talked about, instead of just actual values, raw data, let's look at the sampling distributions, right, for sample means. That is, looking at, if I've got my population, I'm taking various sets of samples and then talking about the mean of those sample means, right? That's what we talked about in section 5.4. And we talked about mu x bar being mu x for large samples or normal populations, and sigma x bar being sigma x divided by the square root of n, which would then you would use for your z-scores and whatnot. Remember that you will be getting your formula sheets, so all of that junk is all on there. Yeah. I'm trying to see if it states it in a weird way. Nope. Standard deviation of the sampling. Yeah. All of that same stuff. Cool. All right, let's get to our review. So here's question 1. Find the indicated area for each under the standard normal curve. I need a z-score table. Okay, to the left of negative 2.03. Do I need to do anything funky when I say to the left of? Nope. So you just look negative 2.03. Negative 2.03. I'm looking right here. Did you get 0.0212? What you guys got?
Yeah.
0.0212. 0.0212. It's the area under the curve. Part B there, between negative 1.92 and 1.07. Remember, when it's between, you just find the two percentages and find the difference. So let's take negative 1.92. Negative 1.92. Right there, negative 0.0274. And 1.07. Turn the page. 1.07, 1.07 over here. 0.8577. Check me as I go along. I'm doing this with you guys, right? Not doing it from a key. So if I screw up, which I sometimes do, I'm not a robot, let me know. 0.0274, not 47. 8303. Is that what you guys got?
Yeah.
0.8303. And then to the right of 1.99, positive 1.99. So I'm going to go here, 1.9, final row of the final column of the row, 0.9767. So to the right of would be 1 minus. Oh, shoot, I already forgot it. 1.9767. 0.9767, right? To the right of that. So we would do 1 minus 0.9767. And that would give me 0.0233. You know, coincidentally enough, or maybe not so coincidentally, you know, if I looked at, let me maybe ask this question. What z-score gives me 0.0233?
It's negative 1.9.
Negative 1.99. Negative 1.99.
Whoa.
So another way that you could compute to the right of is just taking the negative z. Okay? Understand that, because think about it reflecting equally on the other side of the normal curve. Right? If you're finding the area to the right of 1.99, that's like over here, right? You want this area. Well, I find that z-score and do 1 minus this left side, right? But doesn't that have the exact same area as a reflected point over here, which is the true area on the table for that same z-score, just on the reflected on the other side? So if this is 1.99, well, then you just take negative 1.99. So there are kind of two ways to go about that. Yeah, you'll probably always see me do the 1 minus, but either way. Okay, find the z-score for which 60% of the distribution's area lies between z and negative z. I find this question kind of interesting. You want to find a z-score, and it kind of relates exactly to what we were just talking about. I want 60% of the distribution's area lying between z and negative z. So I've got to figure out the z-score where I take the positive and the negative. Same number, positive and negative, right? Negative z and positive z. Same number. And I want 60% of that data to fall between there. What's that really saying? I'm saying, kind of an oblong, kind of an unnormal curve there. Here's my mu, excuse me, and I want 60% of my data here, and here, right? I want 60% of my data to fall between here and here. You follow me there?
Yeah.
So there's a couple different ways we could think about this. My brain immediately goes to this. Well, I know my z-score chart has areas to the left, correct? what percentage am I really looking for this z-score? Am I looking for 30? Am I looking for 60? Neither one of those.
Looking for
Is it
80.
40?
What am I looking for?
80.
80.
Whoa.
Why? Well, because if this is 60, what's each tail out here?
20.
Right? Because I've got 40% left over. So there's 20% here. Okay, I was going for a purple marker, but okay. There's 20% here and there's 20% here. So if I truly want all of this area, what am I looking for? 80. 20 plus 60 is 80. So looking for 80%, 0.84. Right? 0.84. So Z, and that was rounding. I saw 0.7995, right?
Yeah.
0.84. So Z is equal to 0.84. Or plus or minus 0.84, right? Because that's really what I'm asking you. Find the z-score for which 60% of the distribution's area lies between z and negative z. So the two z-scores would be 0.84. Questions about that? All right. Assume the continuous random variable x is normally distributed, the mean and equal to 42. Mu is 42. And the standard deviation, sigma, is 1.1. Find the indicated probability. Oh, not 1.1. 11, excuse me. 11. All right, so standard deviation is 11, mu is 4.2. Let's find the probability that x is greater than 55. I've got to compute a z-score. So x minus mu, 55, minus 11, minus 42, excuse me, divided by 11. All right, so that's going to give me 55 minus 42 divided by 11 is 1.18. Right? And I'm saying to the right of, right? So I'm going to have to take the percent and then subtract 1 by this percent. Another way to do this, just look at negative 1.18. That'll give it to you too. But I'll do the positive because that's probably how you guys did it. 1.18, 0.8810, 0.8810. So that's 0.8810. And again, because I'm saying to the right of, greater than, I have to do 1 minus 0.8810, which is 0.1190. And again, coincidentally enough, if I go to negative 1.18, I get 0.1190. All right, let's take a look at B. Okay, I've got to find both of those z-scores now and then find the area in between, find the probability in between. So let's look at 32. 32 minus 42, x minus mu, divided by sigma. So 32 minus 42, negative 10, divided by 11, negative 0.91. And then we find the other z-score, which is 60 minus 42, divided by 11. So 60 minus 42 divided by 11 is 1.64, rounded to the nearest hundred. So let's find each one of those percentages. Let's go negative 0.91. Negative 0.91 is over here. Negative 0.91 is 0.1814. 0.1814. And we'll do 1.64. Flip it over. 1.64. 9495. 1.64. 9495. 0.9495, right? That's right. Yep. And the difference between the two, because again, I want to find probability that it lies in between, would be 9.9495 minus 0.1814, which is 0.7681. Again, understand what that means. That means if I know my mean is equal to 42, I know my standard deviation is 11. This is randomly selecting a piece of data. Is it going to what percentage chance is it going to fall between 32 and 60? Well, there's about a 77% chance that if I randomly select a piece of data in there, whatever this data is, I don't even know. There's no context. That there's a 77% chance that it's going to fall between those two values, given those parameters. Questions on 3. Let's take a look at 4. Ooh, a lot of things here to do. A lot of things. Surveys of car owners show that the average age of their car is 10.4 years with a standard deviation of 3.4 years. All right, so mu is 10.4. And standard deviation sigma is 3.4. Assuming that the length of time is normally distributed. Okay, normally distributed. That's gonna be key here. Especially part D. If a single car owner is selected, what is the probability that his or her car is between 7 and 11.3 years old? All right, so first thing I got to do is find z-scores for those. So 11.3 minus 10.4 divided by 3.4. So my high end is 0.26, z-score of 0.26. My low end, 7 minus 10.4. Divided by 3.4. Oh, -1. So -1. So let's find those two percentages. So negative. So I got my positive in here. 0.26. 0.6026. 6026. 0.26. Yep. And then -1. -1 flat. 0.1587. 0.1587. Okay, so 0.6026 minus 0.1587 gets me 0.4439. Again, about a 44% chance that if you randomly select a car, that its average age, or sorry, not its average age, that its age is between 7 and 11.3 years. If a single car owner is selected, what is the probability that his or her car is more than 8.3 years old? This was actually easier than part A. More than 8.3 years old. So, or 8.3 years old. And so my z-score is x minus mu divided by sigma. My z-score is -0.62. So I'm going to go here, -0.62 over here. Where am I choosing all the ones that go over there? 0.2358. 0.2358. And can I just take 0.2358? No, I got to do 1 minus because I want to know what's the probability that it's more than 8.3 years old. So 1 minus that thing to the right of 2358 gives me 0.7642. 0.7642. So 76% chance that that car is more than 8.3 years old. Good so far? Let's take a look at part C. A company guarantees that their car lasts longer than 92% of the cars in the market. How long will it have to last to ensure that guarantee? Okay, so now this is when the next section comes into play. I got to look at the percentage, right? So 0.92. 0.92. Now, lasts longer than 92%. You got to think about it this way. Do I need to take the 8% or 92%? Yeah, so 92% is over here, right? 92% is behind us. So, okay, I can just take 0.92. Where is 0.92? 1.41. Yeah, let's round it to 1.41. If you really wanted to, you could say 1.405. But let's say 1.41. So z-score with a 92% is 1.41. So now to figure out the x value, remember x x is equal to mu plus z sigma. So x is equal to mu plus z sigma. Okay. 10.4 plus z sigma. 15.19. So x is equal to 15.19. So in summary here, how long will it have to last? It's got to last more than 15.2 years or 15.19 years. For that guarantee to be solid, to be valid, it needs to last longer than 15.19 years. Now, what's different between parts A, B, and C and then part D? What's different here? If a random sample of 15, okay, so am I choosing one car? No, I'm choosing a sample of cars, right? This is where it gets into section 5.4, the sampling distributions, the sample mean. If a random sample of 15 car owners is taken, what is the probability that the mean age of their cars is less than 10 years? So I want to find, okay, so mu x bar is going to be less than 10 years. Right? That's what I'm going to be looking for. That's probability of that, right? Okay, let's find the z-score then. Now the z-score formula has to change a little bit. The z-score formula has to, you might be thinking, well, wait. That's too small of a sample size. I can't do this problem. What allows me to do this problem? Because it's normally distributed, right? The sample size being less than 30 might have us, have a little cause for concern. And pump the brakes a little bit. No pun intended with cars, right? But because the sample is normally distributed, we assuming that it's normally distributed, I don't care what size sample I have. Okay, so that being said, the formula is z-score is x bar minus mu x, and this was x bar. Sorry, x bar. X bar minus mu x bar. I don't know why I did that. Over sigma divided by square root of n. And that mu x bar is mu x. Okay. Well, that's a really weird looking sigma. So x bar is 10. What was the mu? 10.4 divided by sigma, which was 3.4, divided by the square root of n. What's n in this case? 15. Okay, so I've got 10 minus 10.4, in other words, negative 0.4, divided by 3.4 divided by the square root of 15, which gives us negative 0.46. Negative 0.46. Right? That's the z-score that we're going to use. And I don't need to do anything funky with it because I say less than 10 years. So I don't need to do like any sort of 1 minus or anything like that. So negative 0.46, negative side, 0.46, 0.3228. Good there? All right, let's take a look at number 5. The algebra OST test is taken freshmen. They have taken freshmen. Where did they hide them?
I don't care.
Is taken by freshmen. There you go. The scores are. I have a unique set of skills. I will come to find you. Movie reference, you guys know that? Okay. It just wasn't funny.
We chuckled a little. I did.
Sufficiently funny. Okay. The scores are, I found it more funny than you. Scores are normally distributed with a mean of 700. Standard deviation of 30. I can't let it go. It's been taken. It's like pulling them underneath the bed. What percentage of students should score at least a 682? Okay, which is interesting enough. Like that is the like the score that you need to be, like that's what they call the proficient score. Like the score that you need to graduate. What percentage of students should score at least a 682? So let's figure out the percent for 682. So x minus mu divided by sigma, right? Divided by sigma. All right, so 682 minus 700 divided by 30. Okay, negative 0.6, which negative 0.6, 0.6 flat, 0.2743. 0.2743. Oh, wait. Put it negative 0.6. Negative 0.6, which is, we said 0.2743. 0.2743. Now, do I have to take one minus? Yeah, because it's at least greater than, right? So 1 minus 0.2743 gets us 0.7257. 0.7257. So about 73% of students should be getting this 682 or higher. One of the top schools in the county boasts that they have scores in the top 10%. What score must they have received? So in top 10%, am I going to look for 0.1? No, because they're saying this. We are here. That's the top 10%. So what really am I going to look for here? 0.9. 0.9. 1.28. Looks like 1.28 is closer. Would you guys agree?
1.105.
1.1.
Oh no, that's wrong.
Yeah, that's wrong. 1.28. I'm going to say 1.28 because 0.8997 is 1.28. 0.9015, so 15 10,000ths is 1.29. So I'm going to say 1.28. So this has a z-score of 1.28. Okay, so looking for an x value now. X is equal to mu plus z sigma. Mu plus z sigma. So 700 plus 1.28 times 30. So they're saying that must mean that we have gotten an average score of 738.4. 738.4.
So we don't even talk about the 10% on that problem. We just use the 90%.
Right. Because you got to think about it in terms of, like, remember, this is always showing you to the left. There's no chart for to the right. Make sense? It's just 1 minus this. A random sample of 50 students is taken. Okay, now, I am not just selecting a student. I am selecting 50 of them, right? So n is equal to 50, right? N is equal to 50. What is the probability that the mean of their scores is in between 698 and 705? All right. So now we have to go with the x bar minus mu over sigma divided by square root of n. Okay, so 698. Let's do 698 first. 698 minus 700 divided by sigma, which is 30, over the square root of 50. Okay, so 698, so negative 2 divided by 30 divided by the square root of 50, which is going to get me negative 0.47. So negative 0.47. There's my first z-score, my low z-score. And then let's look at the 705. So same type of thing, but now instead of a -2 up top, I'm going to just have a 5, right? 705 minus 700, which is going to give me 1.18. Okay, so negative 0.47, 0.3192, 1.18, 0.8810, good, 0.8810, and we subtract down 0.8810 minus, oh, I did 3190. 0.5618. So I can say about 56% of the data is going to fall between the averages are going to fall between 698 and 705. All right, any questions there before I move on? I just kind of flipped the side. The mean GPA at LHS is 2.95 with a standard deviation of 0.62. That's not true. I just made that up. You take a random sample of 85 students. What is the probability that the mean GPA of your sample will be greater than 3.15? So am I looking at a single student? No, I'm looking at the sample, right? So I've got to do that again. Z is equal to X bar minus mu over sigma divided by square root of n. Right? What's the probability that the mean GPA is greater than 3.15? Okay, greater than 3.15. 3.15 is my mean minus my mu divided by, okay, sigma 0.62 divided by the square root of 85, which is 2.97. 2.97. That's a z-score. That's a really, really big z-score. 2.97. It's really high. 2.97. 0.9985. 0.9985. But I want to find the probability that the mean GPA is greater than that, right? So 1 minus. Which is really low, 0.0015.
That doesn't really make sense because it's like
It's only 0.2 away, right? But the problem is the standard deviation is so low, right? Standard deviation is so low. So, and because my sample is so big, right? Like if my sample was, the bigger my sample gets, the closer my mean that I get from my sample should be to the true mean, right? So if I said my sample was 300, that 3.15 would be way out there. You know what I mean? If I said my sample was 10, that 3.15 is a little bit more reasonable. Does that make sense? And then part B, what is the probability that the mean GPA of your sample is between 2.82 and 2.99? So let's find the z-score for each. So I've got 2.82 minus 2.95 divided by, and this is where we got, oh, you know what I'm going to do? I'm going to do this so I don't have to retype everything. Negative 1.93. And then I've got 2.99. 2.99 minus 2.95. And I'm going to take this and do that again. Answer divided by that. So 0.59. Okay, so negative 1.93, negative 1.93, 0.0268, 0.0268, and then 0.59, 0.7224. And we find the difference of the two. 0.7224 minus 0.0268. 0.6956. There we go. Questions there? Well, that was fun. That was a blast right there. What else would you guys want to be doing on a Monday morning?